Okay, thank you very much for reminding me to record. I think it was really very clever of you to change your names to don't forget to record or recording today. I think that's very clever. Uh, it's I guess one of the nice things about teaching graduate students in physics is that they're smart and amusing people. Let me tell you what I'd like to do today. I'd like to review, well, first I'd like to answer whatever questions you have. But secondly, I'd like to review what we did yesterday. And I'd like to put, since I forgot to record yesterday, I'd like to put this recording on YouTube because I think that it's easier to download things from YouTube than to download them from the UNM website. So then I would ask you to try to be as anonymous as possible. Let's see, we need to use the chat function. Now, let me ask you quickly a question. Can you see the screen that I'm sharing? I believe that I'm sharing the screen. Oh, yes. Okay, great. And secondly, because electrical surges in the new physics building destroyed the hard drives on my two office iMacs, I have moved all the relevant 466 files, at least I think I moved all of them, to the UNM website, where I have been posting the recordings of the 468 Wednesday lectures. Are you able to see the files by logging into that website? So could somebody reply on chat? Yes, no, maybe, or nobody's trying. No. Oh, okay. Why not? What happens? Could you? Oh, you sent me an email. Okay, let me see where this email is. What was the title or subject? Okay, wait a minute, I think I found it. The new link to the 468 takes me to an empty OneDrive folder with a message, this item might not exist, my goodness. Okay, this is a disaster. I don't know what to do about it. I will try to fix it really soon. So this is another reason to put this thing on YouTube. Let me also ask you, so that seems to mean that none of you have been able to view the, oh, it works. All right, so the situation is confusing because all right, okay, some people are able to see it and others not. So I don't know what that means. Well, let's see. I'll bring it up with the. All right. Let me say this. I wish you would. Right. The folder has one HTML file and a lot of PDF files. I should say maybe 5 PDF files, 1 HTML file, and a bunch of MP4 files. In fact, let me see if I can't even show it to you. Let's see. Right. Okay, I'm going to move the screen over here. This is what it's supposed to look like. So I imagine you can all see that. I don't know. Let me get rid of this thing. So you see you've got some PDF files, an HTML file on which the links don't work because I just imported it from the computer where it was living. And then a bunch of MP4 files. So that's basically the situation. So the HTML is not complete. If I click on the HTML, well, it shows up complete on my screen. I don't know what is going on here. All right, listen, let's get to the mathematical physics and deal with this issue later. So my plan today then is to record this and 468 class, put it on YouTube because the other one wasn't, but I'll put it in both places. Okay, so let me start by reviewing, well, answering questions and then reviewing what we did on Tuesday. And maybe I should even start kind of at the beginning, namely that so let me maybe go to blue. So what we've got here is that in general, well, I don't know if it's actually in general, but very often what we're dealing with is we have something like this, minus grad squared plus over 2m. I'm setting h bar and c equal to 1. I don't think so it would actually be minus h bar squared grad squared over 2m plus v of r vector on psi of r vector equals e times psi of r vector. So this is the equation Hamilton, I'm sorry, that should have been here. Let me see if I can undo that. So what I want here is, this is Hamiltonian on psi is equal to E psi. So this is then, E is then an eigenvalue. And this is the Hamiltonian. And so the Hamiltonian is this. And normally psi is a function of r, or possibly psi is a function of r and t. Let me just check something that's on the stove. I don't want it to boil over. Okay, I think that's all right. So the point is that we start out with a function of several variables, and then what we often do is we change it to a function of r, a theta, and phi. And this in particular is usually some function psi nl of r, and then a spherical harmonic, which is going to be some ylm of theta, and then some e to the im phi. This is typically what we do. So in other words, we separate the variables. And then once we've separated the variables, what we have in general is that psi and y, or psi nl, say, y, lm, and then e to the im phi satisfy equations that are of the form y double prime plus p y prime plus qy equals 0. So that's the overall picture of what we're dealing with. This is in response to a very good question that I got yesterday, but and I sort of answered it yesterday in this way, but I just thought I would repeat that. So that's the general context in which we are. And now to start, the first thing we do is we look at whether this differential equation, so this thing here is actually, let me see if I can fix the penmanship a little bit. This is actually just a first derivative. So the first thing we do is we see whether p of x and q of x are singular anywhere. And we typically call that point x0. And basically is if p is just something like 1 over x minus x0, and how do I've got auto minimize here, and how do I make it go away? Well, anyway, and if q goes as 1 over x minus x0 squared, then one can use Frobenius's method. And so then what we do is we, let me go to this equation. We do a series expansion of the function y as some sort of a x minus x0 to the r, then times a sum n equals 0 to infinity a n x minus x0 to the n. Now, in order to keep the notation simple, it's convenient to jump to the case where just set x0 equal to 0, just to make the notation simpler. And then what we do is we let little p equal to x big P, little q equal to x squared big Q. And so that's this material. And then we have this differential equation. And I can make this bigger, actually. And then we expand y as a power series about the point that's a regular singular point. So this situation here is one in which we say, then this is a regular singular point. Sometimes the sometimes the equation might have no singular points at all. So then what we do is we write y of x as x to the r then times the sum an x to the n from 0 to infinity. If x0 is 0, we're expanding about 0. And then we differentiate once, twice, and we substitute those formulas, these three series, we substitute into this equation. And as I said, this equation is basically of the same form as Hamiltonian on psi equals E psi for one-dimensional problems, but by separating the variables, we reduce everything to a one-dimensional problem. And I was illustrating this for quantum mechanics, H psi equals E psi, but there are analogous equations in the rest of mathematical physics, or such equations often occur. And so what Frobenius showed is that we can go through this and create the series solution. And when we substitute these three series into this differential equation, what we get is a rather complicated expression. And so the first thing we do is we look at the lowest power of the coefficients have to vanish for every power of x, and in particular for the power for n equals 0, which is the rth power. And in that case, the coefficient reduces just to this expression here. And this is called the indicial equation. There are two roots, R1 and R2. And if we want to go further, what we typically do is we expand P and Q as polynomials, at least if they are polynomials. If they're not polynomials, then we have to massage these equations a little bit so that we can write P and Q as polynomials. In this case, P sub 0 is P of 0 and Q sub 0 is Q of 0. In that case, we get that this rather complicated equation becomes a yet more complicated equation, which is a recursion relation. It says that A sub k is dependent on aj, where j runs from 0 to k minus 1. So that means you've basically got the thing solved. It's just that it's very complicated. Now, of course, if you were doing this on a computer, that would be a breeze. All right. Let me, I think, we did, I think, the sines and cosines example before. Let me do the Legendre case a little more carefully. And I think what I did was I wrote up in a little more detail this example. And because it's important, I think maybe we'll go through that, since this is, after all, a Wednesday lecture where we try to do more examples. So the deal is, Legendre's equation is sometimes written this way. I'm rewriting it this way, which, if I recall correctly, is the canonical way that we've been writing things in the Frobenius way of writing things. And so then we just substitute these directly into Legendre's equation. Then we get this expression, which, as you see, is a great deal more simple than this equation. And we've already expanded P and Q. There are no more PJs or QJs. So that's what happens in general, is that you don't get an equation that's this complicated. You get something that's much simpler. Now, the coefficient of the lowest power of x here is r minus 1, a 0. So the initial equation is r minus 1 equals 0. And now the theorem that we talked about yesterday and we'll talk about again today, Fuchsia's theorem, says that, whoops, oh gosh, let me make this bigger. So Fuchsia's theorem says that if the two roots differ by an integer, as they do here, because it's r equals 0 and r equals 1, the bigger root yields a solution. Often you only get one solution, but sometimes you get two solutions. And in this case, you actually do get two solutions. And so I chose r equals 0 because it's simpler than r equals 1. And so I then just substitute in this equation r equals 0. And now you see our recursion relation is quite a bit simpler than this thing, which is rather frightening. Instead, we have this is the differential equation. And then what we do to get our recursion relation, which is actually this one, this is in the examples PDF, which I'll put on the web page that we were talking about earlier. I'll put it on that later tonight. This equation is vastly simpler than that one. And that's typically the case in actual real physics problems where we deal with nice differential equations. Now, to get to this equation, what we do is we shift the index n here on this term, this n minus 1 times x to the n minus 2. We shift n, we set n equal to j plus 2. And then you see the j equals 0 and j equals 1 term actually correspond to the terms here, the first two terms here, which vanish. And so we can do that, make that change. And then what's left in this term and this term and that term, we just set n equal to j plus 2. And in that case, we get these terms here. So n is then j plus 2 there. And at that point, what you get is this recursion relation. I'm just wondering whether I did this absolutely correctly. So I'm going to check this over again tonight, but let's assume for now that it's right. In any event, we then get this recursion relation, and for very large j, we see that it's j squared over j squared. And consequently, it would diverge. In other words, what we're saying here is that so for Legendre, so let me maybe change the color to black now. So for Legendre's equation, we have a recursion relation that's aj plus 2 is approximately equal to aj for j vastly greater than 1. And in that case, the series is I of x starts to look like just simply x to the n times some constant, say a 300 or something. And the result is that this diverges unless x is less than 1. But we want a solution for all x. And so the way we get that is we say, well, in order to have a solution for all x, we're going to say that lambda has to assume a special value, and the special value is lambda is j plus 1 for some j, some integer j. And And so that J then is an eigenvalue, or lambda is an eigenvalue, or eigenvalue. And when we set lambda equal to J plus 1, then the series is a Legendre polynomial. Another example is Hermet's equation. This is actually a more interesting example and maybe a little bit simpler. Namely, Hermet's equation is y double prime plus lambda minus x squared y equals 0. And this, we're talking about the interval from minus infinity to plus infinity. And we first look at how y behaves as x goes to infinity. And the criterion that we mentioned, the criteria we mentioned yesterday, say that that in fact the point at infinity, or the point of infinity, is an essential singularity. But that doesn't mean that we're finished. What we do is we or to put it differently, what does that mean? Well, what that means is, so let's switch then to, let's switch to a different color. Let's go back to blue maybe. And so for the Hermet case, the equation is essentially, for large X, it looks like this. And so this is a hugely divergent as X goes to infinity. So it would say something like Y goes as e to the X squared, something like that, some constant here. And so what we do is we say, well, let's set Y equal to e to the minus X squared over 2. Then times some function h of x. And if we do that, then our differential equation becomes this one here. And this is regular at all x. And little p of x is this, little q of x is that. And p and q both vanish at 0. The initial equation is again r minus 1 equals 0. So the roots are r equals 0, r equals 1. Once again, I chose the simpler root, r equals 0, and we get this differential equation. If we shift n on the first sum, but not the second, we get this differential equation, which gives us a recursion relation, namely that a sub n plus 2 is this thing here times a sub n over n plus 2, n plus 1. Once again, this series would be one where a sub n plus 2 for very large n goes as 2 over n times a sub n for very large n. And consequently, the series y of x for very large n is a sum of something like 2 over n to the n, x to the n, times some overall constant. This is the series for very large values of, these are the terms of the series, past n equals 1,000 or something. And this series, again, diverges unless, oh, wait a minute, do I have this right? Actually, that's an n factorial, isn't it? 2 a sub n over n. Actually, this series may converge, now that I think about it. Oh, it may converge, but it won't be square integrable. I think that's the issue. So I shouldn't have, I need to fix this. It's not that it gives you a function that isn't going to be square integrable. So we set lambda equal to 2n plus 1. And so lambda is an eigenvalue. When lambda is 2n plus 1, where n is some integer, we have the series terminates. And so then we have, this is I guess a Hermet polynomial. And these are the odd solutions because actually, these are the even solutions because there's an extra factor of x somewhere. We get the odd solutions by setting r equal to 1. We then get a different recursion relation like this. And so we eventually get the Hermet polynomials. This stuff is discussed way early in the book. Let me see, I think it's back here. Oh gosh, I don't quite remember where. Anyway, this is a discussion. If you look in the index of the book for Hermet polynomials, you can see where I think it's where I discuss coherent states. Another example that's, of course, very close to what we were just talking about is the hydrogen atom. And then after we've once again turned psi of r, theta, and phi to some r of r YLM of theta and e to the im phi. Once we've done that, the equation for r is this equation here. It has a regular singular point at r equals 0 and an essentially singular point at infinity. And so to compensate at r equals 0, we just let r equal to big R equal to r to the L times s. And then when we substitute into this equation and look at this equation near r equals 0, maybe I should show you that. So we're letting, let's forget the s term. Let's just imagine that s is basically constant when you go r equals 0. So we're saying r as r to the L. So then we have r squared r prime prime plus, and then alpha r squared plus beta r plus gamma r equals 0. Well, r prime here is going to give us L r squared r to the L minus 1. And then we have to differentiate that, right? So I think I did that right. And now if we differentiate a second term, what we get is L minus 1, r to the L minus 2, but then that's r to the L. And what's the rest of it? Well, the important terms here, the important term is this one near r equals 0. So that's then plus gamma r to the L equals 0. So gamma has to be minus L minus 1, which is this equation here. To deal with the essential singularity infinity, we just say, well, S is going to be e to the minus delta R times some little s. And then, well, let's look at the equation then at near infinity. Well, the equation near infinity, well, one has to do this more carefully at this point. in other words, we're setting R equal to R to the L, e to the minus delta R times delta. That was an R, so let me just, all right, let me just undo these. E to the minus delta R times little s. We take this and we substitute into this equation, and we then find that delta and alpha have to be related in this way. So then at that point, what we have is that this is equal to R to the L, e to the minus square root of minus alpha R, and then S. And then what we do is we use Frobenius to find out what this is. In other words, we substitute into this equation and then we evaluate what S is. Okay, so let me go on to Fuchs's theorem. Oh, maybe I should say, well, I think I've said enough about that. All right. So Fuchs's theorem, and what Fuchs said was that showed was that if you apply the method of Frobenius to a second order linear homogeneous ODE about a regular point or a regular singular point, you always get at least one power series solution. If the roots are equal, you only get one. If the two roots, and it's obvious why you only get one, because you just have one equation and one recursion relation. If the two roots differ by a non-integer, you get two solutions. If they differ by an integer, the bigger root will yield a solution and the lower root may yield a solution. And it turns out that if you apply Frobenius to Legendre's equation, the roots R equals 0, R equals 1 lead to the same solution. On the other hand, for the harmonic oscillator and Hermet's equation, the two roots lead to two different solutions. If you look at this expression and just do the differentiation, we see it looks like this. If you now let x go to minus x, you get this expression here. This tells us that this differential operator transforms as -1 to the n minus p times itself. And so then you can analyze a second, what happens to a second order linear differential operator under reflection, and then you can see, well, it can be even or it can be odd. In general, it's neither even nor odd, but what you can do is you can split it into an even part plus an odd part. The equations of physics are very often have differential operators that are either even or odd because they are particularly simple differential operators. Remember that that Wronski's determinant is if you have n functions that are linearly dependent, then there's a set of coefficients non-zero so that this sum vanishes for all x. If the functions y are linearly dependent and not all the k's are 0. If we now differentiate I terms, we still get 0. And so what we have then, if we construct this matrix of derivatives, the I minus 1, the ith row consists of the I minus first derivative of the various functions yj. And then what we can say is that if that since y maps k to 0, the columns are linearly dependent, and so the determinant must vanish. This is something that we talked about back in the first chapter, equation 215, I think. And anyway, this thing is called the Wronskian. And you can tell then whether or not the functions are linearly dependent. And it vanishes if and only on an interval, if and only if they're linearly dependent. And Wronski had a, Wronski's invented, one can use Wronski's determinant to find a second solution to a second order differential equation. So remember, if we use Frobenius and Fuchs, we can find at least one solution as a series expansion about any point that's regular, a regular singular point of this differential equation. And so let's imagine for a moment then that y1 and y2 are two linearly independent solutions of this equation. Then the Wronskian doesn't vanish, except perhaps at isolated points. But now if you compute the derivative, you get this, and you find that when you then substitute for the second derivatives, this differential equation, the q terms drop out. And so you get that the derivative of the Wronskian is minus the p term times the Wronskian, and that's something you can integrate. And so this is Abel's formula for the Wronskian. And once you've been able to express the Wronskian in terms of p, so you know what the Wronskian is, you then notice that the Wronskian actually is the square of the first solution times the derivative of the ratio of the solutions. So you can rewrite this as a differential equation for the ratio, and when you integrate it, you get a second solution in terms of the first. So that means that using Frobenius and Fuchs, we get one solution for the equation that we need, and for the second order homogeneous linear ODE. Then having that first solution, y1, we can use Wronski's trick to find y2. And so we always get two solutions. The reason you don't get three is that the third order Wronskian would look like this, and we would, so if these were three linearly independent solutions, this thing would not vanish, but we know it does because y double prime, yj double prime is related to yj prime and yj, and so we get an expression like this, so the Wronskian identically vanishes. I think we can skip the rest of this. If we have then a second order differential equation, we get two solutions in general, and to determine the constants of integration and so forth, and make to get a unique solution that's appropriate for our boundary conditions or our particular physical problem, what we have to do is apply the boundary conditions, and for a second order differential equation, we just apply the two boundary conditions. So I'm going to go through this. Let's see, I haven't had a chat question in a while, and I don't think I should just barrel along without some guidance from the students. Is there something you want me to, discuss rather than just to go over what we did yesterday a second time? Well, I'll keep barreling along until I see something in the chat window. I'll move the chat window though a little bit closer here, so it'll catch my, so I'll see it. Oh, a hint on problem 635. All right, let me grab the book and look at problem 635. Well, okay, this is, so let's just look at what this question happens to be. let's switch to red. Whoops. So let me just draw a couple of lines here. So what we're doing is we're integrating something like e to the I k over k dk, and it's a contour from L.
Cahill, we can't see your notepad.
Oh, Christ. Thank you. Whoever you might be. All right, let me get rid of this. Okay, what are we doing then as an integral here? We're integrating from L to L plus IH, and then right, okay. So what we're doing is we're going from minus L to L, up to L plus IH, then we're going this way, and then down. So it looks like this. And this is minus L plus IH. And we want to show that this is actually equal to 0 in the limit capital L and capital H go to infinity. Well, all right, so let me just think. I'm just wondering if there's a cute way to do it. Actually, there may be a cute way to do it, but let me not do the cute way. So what you need to do here is, first of all, let's let k equal to, let us say, x plus iy. And so then over here, let me switch colors here then. So over here, what does this look like? This looks like e to the I x plus iy divided by, and if I'm just looking at magnitude of the denominator, it's basically square root of x squared plus y squared. And then we're integrating along a distance h, so it's altogether an h there. But x is equal to L, so this is e to the I L plus iy divided by, so for practical purposes, this is h over L. And so if you can do the y integration approximately, and it's just it's a finite integral, sort of 1 minus e to the minus h, I think, essentially. And so let me think. I think the way I was thinking of this was that h, well, let's keep h, I think maybe I should have said keep h finite. If we keep h finite for the moment, we can see that this goes to 0. If we imagine taking the limit such that h is always very small compared to L, then in other words, something like L is equal to, say, capital R to the 4th power, say, and h is just equal to capital R. And now we take the limit as R goes to infinity, then this thing is going to vanish. And maybe I should, in as much as you want more of a, oh, yes, yes, all right. So there's a statement about the, so here, let me fix this. Yes, I went in the wrong direction here. And so this is actually like that. Let me bail out here by looking for the solutions. So let's see, file, open recent. Okay. Where is it? All right, over there. Over there. Okay. And so let's see, it's all right, it's closer to this. So this one was this is 35. So let me see what I did here. Oh, it's 630. Sorry, I'm in the wrong chapter. Yeah, okay. So actually, one has to use more care. One can't do it as simply as I was saying. So let me show you what one actually does. So the integral along, I mean, all right, let's just go back to see what it looks like. The exponential looks like this. And so the integral on the upper contour is going to vanish. So this, in other words, this integral is going to vanish in an obvious way because it's e to the minus h. In other words, this y is equal to h, and so it's like e to the minus h. So the upper integral vanishes. So in other words, this integral is like e to the minus h, and so that one vanishes for that reason. If we look at the right vertical contour, so I sub r, then this is an integral doing it exactly. It's 0 to h. Whoops. E to the I L plus I little h d little h over L plus I h. And if you do that thing exactly, what you see is that this is equal to e to the IL integral 0 to h of e to the minus h dh over
Dr. Cahill, can you move your Finder window out of the way, please?
yeah, thank you. Okay, L plus IH, and then we can bound this, and it's then 1 over L times an integral 0 to h of e to the minus h dh, and so this is 1 over L times 1 minus e to the minus h. And so as you let h and L go to infinity, this goes to 0. So doing this more carefully, you see that. Actually, that's the way I wrote up the solution. So let me just read the problem again. I think I misread the problem. So it's the integral along the contour from k equals L. So we go up, then we go down. Oh yeah, all right. So the contour is much simpler than the one I was thinking about. Well, it's not much simpler, but it looks like this. This is the contour. So this term vanishes. So this part of the integral, let me just go to blue then for a second. This part of the integral vanishes because just as basically e to the minus h. And so that's kind of obvious. This part vanishes because of this region. And this part also is that you apply the same analysis. And the integral along the real axis is not part of the problem. So that's why that one is not. Okay, there was a question from don't forget to record, which I think is great. The question was, why is k replaced by square root of x squared plus y squared? It's because I made a mistake. It's supposed to be just replaced by L plus IH. Over here, this was dumb. And so let me try to undumb it by saying that this really is so this is really L plus IH. If we're on, I'm not sure where we are at this point, but it's here, let's undo that. It's really x plus IY. But anyway, forget this analysis here. This was too sloppy. The right way to do this is to, first of all, notice that the integral on the top part of the contour vanishes because we have this e to the minus h here. So this goes I times I is minus 1, y is equal to h on this upper contour here. And consequently, this goes as e to the minus h. Maybe I should do this in more detail. In other words, the integral from L plus IH to minus L plus IH, what we're talking about is e to the I x plus IY over x plus IY, and we're going dx. But y is equal to h, and so this is equal to an integral e to the ix minus h over x plus IH dx. And so this is something like 2L times e to the minus h. And so that goes to 0 because exponentials always dominate linear terms. So that's why the upper part goes. The right-hand side of this, the right-hand side of that is requires this more accurate analysis. So basically, with ghost contours, what you do is you eyeball the thing and see if you can find an easy way to do the problem. And if not, then you have to do the problem more or less accurately. and analyze it that way. So let's see, there was a question about 7.2. So let me find 7.2. Well, this is one of those change of variables problems. And the reason you don't, well, first of all, the Bessel function is defined later in the book. Bessel functions are in chapter, what is it, chapter 10. So there's no issue there. But Bessel functions are complicated. And what you want to do here with, by going back to, let's see, all right, let me get to the right place here. We're talking about differential equations, and it should be let's see, 726. Oh, all right, so I've gone much too far. 7. Okay, so the deal is that you you assume that your Jn of x satisfies this equation. And then what you want to show is that Pn, in fact, there shouldn't be a K here. Well, yeah, there should be a K, I guess. P sub Kn of rho, which is defined as J sub n of K rho, satisfies this equation. And so that's what you have to do, and that's basically a change of variable problem. And so just set P equal to that and substitute into this equation, and then you'll get something sort of complicated. You simplify it and you should be able to get this equation. So that's what you're supposed to do. And you're right, it should be P sub Kn. So that's actually a typo in the book. Let's see. What I need to do to get to the exercises. This is 7.2. So let me fix this. This should be P sub okay, so let me correct it here on the fly. So in other words, Jn of Kr and Jn of x satisfies the equation there in the book. So, you assume that Jn of x satisfies 7.26, and then you need to show that P sub Kn of rho, defined as Jn of K rho, satisfies 7.25. So that's one of the standard you know, once my typo is fixed, that's basically a standard change of variables problem. So let's see, do we have any more last minute questions? All right, so I think maybe we'll okay. Hold it. There's a question from Don't Forget to Record. Hint 478. Well, I mean, this is this is meant to be. Oh my gosh, I've got a call from my oldest son here, and that's his son Liam. Hi, Liam. So in 7.8, basically you go back to the example. Okay, yeah, call me later, and that'd be great. This class is almost over, though. It was supposed to end 10 minutes ago. Okay, thanks, Mike. Bye. So the deal here is that you just go back to the place where this was discussed, which was when we were talking about, let's see, examples. I can't quite remember. Ah, there it is. You go back to you look at example 7.30, and basically you just apply 7.30 to do 7.8. So that's the hint. So let's see, any more questions? Okay. All right, so maybe we should end it here, since I've kind of run out of gas. On the other hand, let's see, there was this variational problem. Maybe I should talk about this for a minute, that we discussed yesterday. Basically, suppose you ask, for what functions u is this functional stationary? That is to say, for what functions u is the change in u due to a small change, I'm sorry, for what functions u is the change in e due to a small change in u of second order in the small change in u. And if you write that out, you see that the first order change that you want to set equal to 0 is then this. And so basically, if you're saying that this vanishes, then for all small changes du, then you need that that u satisfies the differential equation and the boundary conditions. If, on the other hand, you say, well, I just want E to be stationary with respect to variations that vanish at the endpoints, then you just get the differential equation. And so then this is a differential operator that's formally self-adjoint. This is the form that it takes. This is a particularly nice form because if L is in self-adjoint form, then it's ready-made to integrate by parts, and then we get Green's formula, namely that the integral of VLU minus ULV is P times the Wronski, the difference in the Wronskians at x equal to B and x equal to A. And if you differentiate this, you get Lagrange's identity, which is that VLU minus ULV is the x derivative of PW, P times the Wronskian of UV, P being this function here. And so that once you put it in formally self-adjoint, when you put it in self-adjoint form, you then get Green's formula, Lagrange's identity, and then you conclude that the differential operator is symmetric, or if it's complex, then it's Hermitian and self-adjoint. And then there's this business of self-adjoint systems. I think that this was rather complicated, but the basic idea is that a differential system is self-adjoint in a way that satisfies mathematicians. If the differential operator is formally self-adjoint, you have a space of functions that satisfy the boundary conditions, and well, these vary. It's a little bit technical. I think maybe I'll just review this next time. Because it is just a bit complicated, and I don't think I ever use this again in the book. Anyway, so what you've got, these are the boundary conditions that one would have, and so basically, a differential system is regular and self-adjoint. If the differential operator is formally self-adjoint, the interval finite, P prime and Q continuous real functions of X on the interval, P always positive on the closed interval, and if the domains coincide. Well, the domains are, the domain D is the set of functions that satisfy the Dirichlet or Neumann boundary conditions, and then the adjoint domain is the domain such that if the adjoint domain is a set of functions V that make the boundary term vanish for all functions U that satisfy the boundary conditions. And so if D equals D prime and everything else is true, then you have a self-adjoint differential system. As I said, this is kind of, this is more appropriate in an applied math course than in a physics course. But the nice thing is that in that case, then you have these, you have as the operator is symmetric, or if it's complex, then it's Hermitian. And okay, is there a final question? No, so I guess I'll say goodbye until tomorrow then. I'm going to put this recording then on both YouTube and on the class website, and I'll update some of the files on the class website. So I think, unless there's another question, I think I'll stop sharing and end and